Okay, let's take a look on how to actually this PSoC creator works. It should be on your workspace here. On the other hand, if you didn't install the shortcuts, then it's you just type PSoC. Usually it gives you the best match, which is PSoC creator application. There, open it. PSoC creator. Actually, there is an update for the PSoC creator, so the current version is 4.3. On the other hand, I'm using 4.2 now, so it's up to you if you use 4.3. It has some a little bit different things there. Mostly just added some the components there, and also improve the performance. And it has support for the exciting new PSoC. Haha. Okay, let's see. The start page looks like this. It actually also is the shortcuts for the recent files. Under start, there's a create new project or open existing project or find code example. Then there under kits, there are actually the sample programs right here, or sample projects. Feel free to use those if you need. Okay, there's also getting acquainted and news and information kind of things in this view. Let's create a new project from scratch, just for fun. Next time we will be creating the project using something else, like a template. Okay, select project type. Basically, you have either a target kit, but okay, that's the we have that kit here, or you can also check the target device. If you use the target device, then you have the PSoC5LP and the processor type is CY8C588L. Okay, it's up to you to decide which one to use. I think that's the easiest way. Select the kit you have and click next. Okay, you can start from the code example, which actually gives you those 3 code examples. They were also under here, this ADC and WART, or blinking LED, or HID mouse. Template project, actually it means that you have a working project and you want to continue from that. Okay, earlier I told you something about making this kind of gradual the development, so part by part development. If you have a bigger project, then you probably want to have say working copies while you are working on it, so that the way it is to save a project with as a template, and next time you go and start from the template. Okay, or well, now we start from scratch, so empty schematic. Okay, workspace name, something descriptive. In your case, I would go with your login name on the system. For example, what is your login name, or some other ID, for example, in Google services or something like that, and then exercise or PSoC Exercise1 workspace name like that. Actually, it does not hurt if also the project name is the same, and if the project actually would be on a location looking like that, or on the other hand, I think it creates the working space under the projects now using that one. So okay, in that case PSoCDesigner course would be a good location for workspace anti-KP PSoCX1, and project name would be that the same. Let's see what does it actually do. Okay, that kind of settings. Click, clock. Whoa, that doesn't look anything familiar with any other development tool. It starts from schematic, electronics schematic or engineering schematic. So this is just a space for making the system design by using symbols. Then on the left hand side there's the workspace explorer showing what is currently on the this project. So there's the top design and then design-wide resources for this project. Then it also shows the current header files and source files. So all the source which is required to build this solution is right there. Okay. On the right hand side there is always hidden the resource meter. It shows how many resources you have used compared to how many resources they are available. These exercises actually you are not running out of these resources, but on the project you may actually take a closer look at some point if you are running low on the resources, and then you can try to find different ways to free some resources. Okay. It also shows the amount of CPU, the memory what you have been using, so especially the EEPROM currently non-used, and yeah, that's it. Then the output actually shows, for example, the compiler messages here. It shows the if you have some errors on the code, you just double click it here, then you can find the what was the place on the code on on your programming or program design window. Yeah, but here on the right hand side there's a component catalog with 202 different components which are divided in 10 different categories, in addition to off-chip components which actually are just symbols for this design. So in addition to the internal components inside of the chip, you can also do the design for the external components. Okay, but this external components design, it doesn't go anywhere. I think you can get a list out from the chip pin out a connection list that could be imported in some electronics design program, but I haven't used that one at all. So, but anyway, so on the component catalog on Cypress, 10 different categories like analog components, and here something like, for example, mixer, meaning analog multiplexer, or yeah, mixer is actually more like, you know, different channels, audio channels in, and then you have a mixed channels out. Then there are the different A to D converters, different type of amplifiers, like just operational amplifier, or well, this is more useful, it's a programmable gain amplifier or inverting or programmable gain amplifier. Analog multiplexers, yep, that's what I was mixed, the mixture. So analog multiplexer is a channel where you can choose an input channel for A to D, for example. Comparators, different types of comparators. D to A converters, current D to A or voltage D to A, or manual routing. Okay, how you route a signal manually from one analog device to another analog, or not device but component. Then a separate system for capacitive sensors. So this is CapSense, CSD. These processors have the capability of capacitive sensing directly from pin. Then there are some communication blocks, like, well, CAN controller. Then this I2C or SPI, there's UART, there's also USB, but as I told you earlier, USB is not part of this course. Okay, communication blocks. Then we have digital functions, logic, registers, utility. Okay, so for example, we have shift registers, PWMs as functions, or just simple logic. So practically the logic gates are here, basic logic gates. Registers, access to registers. A lot of these components actually are so that there's, well, these components are based, of course, on registers. Remember the three-layer three-layer picture of the architecture. So lowest level was the CPU level layer. Then we have this next layer is the digital blocks and analog blocks. And actually all of these blocks have control and status registers. Every single one of them have a register and that's how they are programmed and used. Okay, this here, the component catalog, gives you easy access to each of those registers. You don't need to go and think of which register to write which bin, or which bit to write in which register to get a programmable gain amplifier, for example gain 2. Okay, so everything is actually right here, what you need. So these components, let's take some component. For example, on exercise 1 we need digital output pin. If I take digital output pin here, just add it at the middle. Okay, all right, expand it a bit. So I have one single pin output. That's out on the design. So that was just dragging and dropping, by the way. Then we can see the datasheet for that component. Let's open the datasheet. Okay, there we have a datasheet. What datasheet actually has all the everything. So features. What kind of features does it have? Ready setup of all pin parameters and drive mode. Yep, sure. So this is a component. Then it has some general description, input-output connections. So pin actually can be either pin or bus. Component parameters, how to set up those. Application programming interface, like general API. Okay, let me see. Let me put that one on the side. I don't need that. So, for example, pin read function. You can use this pin this function to read a single pin, or pin write. This was an output pin. So pin write would set it either 1 or 0. So this actually does all the masking and shifting of the bits appropriately without side effects. So a very typical way of demonstrating the side effect on microcontroller is actually have a say low level access to microprocessor pin. If you write your output pin so that you read the input register values actually can affect so that you are also setting a value to the a different pin. Okay, that's a typical example of side effects. This API function is designed so that it does not have that side effect. Okay, so write or read data register or whatever. Okay, in case you are using pin interrupt, you also have the clear interrupt, but more about the interrupts on the next chapter. Okay, so we have application programming interface. There is also a section for sample firmware source code, but on the other hand, most of these are actually PSoC creator products, many example projects. Okay, sure, that's nice. Another thing, okay, there's API memory usage, meaning that how much memory this component is actually using in flash or static RAM. Okay, there we have the PSoC5, and we are using GNU compiler, and the default with interrupt means 112 bytes for the API functions. So that's how much flash memory this component actually takes. Okay, and then there are some details also, so there's plenty of information, and yes, and of course DC and AC characteristics of the real pins actually, and what kind of pins are you using. Good, so in any case, so the data sheets for each component is available just like that. Next important thing is the naming convention. Let me open this one. So double clicking actually gives you access to the configure. So if you name this one, this is an output. If you name it as LED or BLED, for example, whatever the name you have here, that actually also defines the API names. Let's go back to the datasheet and to the API. So basically now we are not calling pin write anymore, but we are actually calling, in this case we would call BLED underscore write. So this the name of this component, the real name of this component actually will be defining also the API function names. That's easy to remember actually. So this way you can have a different name pins, and each of those have different API functions. Okay, then now we have a pin output, which I call BLED as digital output, but okay, this is a very misleading button. It says HW connection, hardware connection. Of course, pin must have hardware connection, but not in this case. this hardware connection, what they are referring here, is actually the internal hardware connection, meaning they are inside of the programmable system chip. For example, hardware connection to a gate output which drives that pin. Okay, so if you have software controllable pin, then you need to unselect the hardware connection. Same thing actually happens in quite a lot of these, for example, communication blocks. You might actually get error messages about they are not having a pin connected. Then you need to go go to this component configuration and take a look what it is. But anyways, yeah. So which kind of type? So digital output in this case. It also has selection for analog, digital input, bidirectional, external terminal. Okay, yeah, but anyways, in this case, this is the digital output. Output enable. Well, if you want to have output enable, the enabled separately by software, yeah, then you would use this output enable. Okay, drive mode. What does mean drive mode? Strong drive means push pull, like in here. So it has push as P FET and pull like pull actually using the this N-channel FET. There are also some other ones like open drain drives high. Okay, so actually it has weak zero state, but actually it can only support it supports only the output high signal has some current, but at state 0 it does not give any or get any current. On zero state that would be actually that will be high impedance. Okay, and some others like resistive pull up, that might be actually quite useful sometimes. Resistive pull up means that you have the initial high state 1 driven by this resistive pull up, but you can run it to low on by the drive here. But anyways, let's go. This is the LED output. So okay, I would say strong drive or open drain with a high drive, either of those. So strong drive is the easiest. That's the push pull totem pole kind of drive, and initial drive state 0. Okay, this is not my favorite kind of design, but there is actually a reason why it should be like that. Is under the let's see, where do I have the schematic of development board. Schematic. The LED on schematic is actually right here, so we can see. Okay, LED has the resistor 820 ohms and the LED on series, and actually it is driving on high state. So logic 1 drives the signal. All right. On old school design, you would always put this LED tied up to the power and use a pulling down kind of drive. But as I said, it would be an old school design. Usually these processors or other devices, they have better drive on to the ground than well, better drive as a sink than as a source. Let's put it this way. Okay, so yeah, so this far we have strong drive, low, initial drive state is 0, so it doesn't blink unless I tell it. Okay, what else? Then we have the output. Okay, what kind of output is it's a fast? Yeah, why not? If you don't need fast signal, then basically you can use different ports. This affects mostly on which pins you can use. Drive level, okay, well, most probably you will drive it to the VDD IO. Current, okay, all pins can actually source 4 milliamps and 8 milliamps syncing. Okay, there you can see also some of the ports. As SAIO ports are capable of syncing 25 milliamps. So in case you had a bright LED, you would actually drive it. Drive mode would be something that syncs that 25 milliamps. But yeah, that's just fine. 4 milliamp source, 8 milliamp sync, fine. Transparent mode, yes. Transparent means that the port the pin actually goes on immediately with the software. Does it, or if it's a single sync, it means that it changes the state on the next sync signal, and sync actually is syncing it to the local oscillator, the high-speed oscillators. All right, mapping, contiguous, yeah, forces placement in adjacent physical pins. Okay, this is fine-tuning. You can actually fine-tune if you are having more than one pin on one bus. Okay, this would be good. You will be display as a bus. Contiguous means that if you are using this as a bus, you need to use actually the adjacent physical pins for output. But that's more or less a advanced kind of property. Okay, power on reset. Which state you would like to have it when you have power on reset? Usually you don't care, but I would say on this case, when it's a source, I actually would use either high Z analog initial state during the power on reset or pull down, since otherwise it could be, for example, pulled up, and then you would be drawing current from the device when you are doing power on reset. That's not a good idea. Okay, some building stuff. Usually you don't need to touch these. Okay, good. So now we have the one pin output, digital output defined as B-LED. Let me apply that. Okay, there we go. That's configured. Next step, since this is pin output, you go and do some pin definitions. Wow, there's a name without a port or pin, and that's supposed to be on 2.1. Okay, was it like that? Exercise 1, pin output. Okay, connect it to pin 2.1. Okay, which is connected physically to blue LED on the board. And okay, we can go next and write a piece of code to blink the LED. Ha! Where do I do that? And what should I do to get the API? I don't see any API functions yet here. So after you have done this definition. So in this case we have the digital output pin, configured it as it is here with a new name BLED, and then we also allocated the pin 2.1 as the physical pin. Okay, what is the next step is click this button on the top corner. It says generate application. Click, and this output actually shows some, okay, there are some synthesis done, routing, lot of stuff happening on the output port, and wow, I got more code. And okay, I have plenty of code here, and basically this comes on the CI boot. Okay, you can figure that out. CI boot actually has the code which is used for booting the processor chip, which has, well, plenty of code that you almost never need to touch unless you want to mess up the system. Then there's the EEPROM based code. Usually you don't need that one either, unless you are using the EEPROM as the temporary non-volatile memory for the device. Then we have plenty of code here, which also is something that you don't need to touch. There are a couple of functions that you may need to touch. One is the main. Well, of course you need to touch. That's your program. Another one, actually there will be these modules. I have the BLED module here, and I have the BLED.h, which defines the prototypes for the functions, and also defines these defines. Yeah, so that's the basically, well, we can open it. So actually it defines the write, set drive mode, set data register read, read, or that. So basically these are the function prototypes for the output pin called BLED, and these basically are the what you can then use to call in the main. Okay, what else? Yeah, then we have some set of constants like, okay, drive mode constants, digital port constants, and such kind of things. But okay, this is a good place to take a look at the references, what things are defined. But usually, well, I would just leave it closed. The BLED.c is something that you almost never need to touch unless you are actually doing the interrupt. Then you can touch this one to make the calling to interrupt service routine. But in this case we have output pin, no need to make that one as interrupting pin. But this has basically the function descriptions for all of these functions needed. Okay, good. Okay, let me close that one, we don't need it. Okay, your own code goes to main.c. And isn't that nice? It basically shows the what you write there, your company, the year. Actually, you could edit this one and copyright your name and which company in that. And then year, all rights reserved. and yeah, unpublished license software, that's just fine. Yeah. Okay. And the copyright description actually could follow either very, confidential proprietary or, how about license software, and then make it a, okay, how does it go? Let's take a closer look. Oh, wow, CC by NCSA. So, come on, Creative Commons licensed by a person, a non-commercial and share alike. Share alike things, so let's go there, and that's my favorite, CC NASA. Was it like that? Let's see. CC by SA. Okay, let me take a closer look how to make it actually. F4.0. Okay, Creative Commons. Share alike. 4.0. Okay, yeah, but anyways, I usually follow that. I just add that one as the commercial or the copyright sentence. So basically this is it's okay to share as long as you don't make money. So for academic purpose, that's just fine. All right, the main.c. First question and then the answer. Do you need to always include this? This includes here. No, you don't. They will be automatically added. All the component library includes are added into project.h. So that's all you need to do is just keep that project.h here. Okay, what next? Then actually that's a perfect for the as a program core right now. So usually on any of these bigger processors, there is always some interrupt driven functions going. At some point you would be turning on the global interrupt enable. If you remove this line, none of the interrupts actually work. So just keep it. It doesn't hurt if it doesn't have any interrupts, just fine. Then there's not just interrupting routines. But anyways, you need to have this one there. Okay, then what next? Wow, place your initialization startup code here. What to do for the initialization of startup? Actually, let's see what components we have. We have that, oh, sorry. Components would be showing here, but the documentation, interesting why it doesn't show the documentation for the, okay, LED. Okay, so let's take a look at general API of that function. So there's only pin write. Some components need initialization. Pin does not, mostly because those functions are actually just a shortcut to macros to set pins on registers. So basically what we need is pin write function, and we don't need these here. We are not interrupting, and usually you would be setting the drive mode on the component editor, but on the other hand it also gives you a possibility to change that drive mode by software. All right, okay, so CY global inter, that's fine. Place your application code here, for example, like that. We have the B LED function or the component, and there we have the write. Write either 0 or 1 or something that changes. Okay, I will just add some value here. For example, blnk, and as you can see, this actually shows already as you write if there are any errors. And yeah, okay, then you go on the top of the error and it says what is the problem here. Undeclared identifier. So undeclared identifier, maybe we can do the description here. So I will just uint 8 type variable blnk, initial value is 0. Okay, so now that command would be just writing the blank there and with only that one, but actually the easiest way of making it to blink would be add it by 1 and then the division remnant to 2, so this gives either 1 or 0 every other time. Okay, small detail. Yeah, forever loop, that's the best operating system on the world. But anyways, this would loop as fast as the processor goes. And the processor actually, I think it was 133 megahertz processor clock rate. That's quite a lot. So maybe we want to slow down this a bit. And there is actually a way. CY. Delay, sorry. Delay, different of CY delay functions like, but CY delay is actually nice. So basically the parameter is how many milliseconds delay you would want to put there. For example, if you have 500 millisecond delay, then basically this one changes the state between 1 and 0 every half second. That's it. So that's how you get it to blink. In principle, this is the first step or task 2 already done here. And next step would be to build the project. Click build. Okay, what building does is actually compiles these source files and also makes the this starts from the design files, the pinouts, and it makes the boot code and everything there, and basically now we have an executable. And we can take a look at the resource meter. We have 0.5% flash use. This program uses 3.8% of static RAM. That's fine. It looks like it fits quite well. We are using 4 pins out of 48 pins. Okay, I used only 1. On the other hand, there are also 3 other pins that are used by the debugging and basically also the yes, in principle it's the debugging that takes those 3 other pins. Okay, next step, program. So when you click this one here, let me open the camera. Okay, let's take this one here. So there's a power LED and status LED. Actually, that green LED here is a status. So when you start programming, let me start programming. So yeah, actually that status LED is actually blinking, showing that it's programming. And after it has programmed, then it starts blinking. Okay, it looks like it works. Good. What's next? You can actually also run the code as debugging mode. For example, you can set a debug breakpoint, for example, on this place. Okay, breakpoint, and say debug. So it programs the system again. Okay, main.c, and we are at the beginning of the code, and then resume execution, goes to that breakpoint. On the breakpoint, you can take a look at the registers, which might be interesting, but actually it also shows the value of that variable, local variables there. So local variable is now changing, adding by one on each button click, and actually that also shows us if the okay. But anyways, this is how you run a code and check in the variables on debug mode. In order to edit this one again, then you need to click stop debugging. Then you can edit the code more. Okay, so that's how you write this simple program using these parameters what we have, or the functions what we have. Also some the example how to do debugging. Okay, the next part actually on the exercise is the pin input. Okay, this is something you can, most probably you can do it already. If you have some trouble getting started on this one, start actually asking questions from each others on some social network. This is basically the same as writing a port, except then now you just configure it differently. You make it as a input port, rename that pin as a button, connect to port 2.2, use the API again. Okay, general API. Input you can read by pin read. Simple. Connect to port 2.2, check the schematic. Let me see, where do I have my schematic? Okay, I don't have it anymore here. Let me open it here. Check the schematic, how it's connected. Now actually we have the push button is connected as grounding connection on an empty, on pin. So you need the pull up resistor, and that you do by configuring this input pin correctly. Okay, and then it would be low active pin. Okay, and then you need to modify the pin that the LED blinks only when the button is pushed. Okay, so meaning that if the button read actually gives you 0, then you would be blinking, continue blinking, otherwise just looping forever. And yes, hint, you can find the API functions from the datasheet. Okay, task 4, simple word communication. I will make another video on that one, although it will be short, but I think well, again, I promise to keep these as short as possible and not shorter than that. So I will continue on task 4 on the next video.